Scientific part of the session. First talk is a talk by Ben Allanach, who is a local here, and he's the experimentalist of the. So the point is that he will tell you what you should predict. If you know the result, it's easier to make the correct prediction. In that sense, I hand it over to Ben.
Okay, thanks. Okay, can you hear me on the microphone? Yeah, that's good. All right, so as Hans-Peter said, it's much better to have someone who doesn't know what they're talking about to tell you about these things. And so really, I can't review, of course, all of experimental physics for you, so I'm just going to review some recent points of interest that have happened over the last year that will hopefully impact the direction in which you're heading. So these are the list of the topics I'm going to cover. I can't give this talk without talking about the Higgs somewhat. And of course, searches for supersymmetry, because most of you are building models which end up as a supersymmetric field theory. There's this result from the Tevatron which disagrees with the standard model. So I want to talk about that. Some recent results in B physics which could be relevant for supersymmetric models. This 130 GeV dark matter line in photon spectra I'm going to mention because that could be relevant for you as well. And then Bay recently kind of finished off finding out what the last neutrino mixing is in the 3 neutrino model. So if you're building models of fermion masses and in particular neutrino masses, that could be useful for you as well. Okay, so let's go to the Higgs. As most of you, or nearly all of you, I'm sure, know this story. So here we have the famous Brazil band plot. On the vertical axis, we have the limit, the upper limit on the cross-section compared to the standard model cross-section. And what you see here in green is the experimental result from Atlas by combining all the different channels that you have. This is still preliminary. From about roughly 5 inverse femtobarns of data. And what you see is that where the line goes below 1, the model's ruled out to 95%. And so you have this island left between, say, 122 and 127 here, which is still alive. There's still a little 1 GeV window here. And if we go over and see what CMS says, they've also got a similar picture. And for the expected signal, the expected limit, in the absence of a Higgs signal, you see this dotted line. And so here, the experiment's not excluding as much as it thought it would. And of course, the reason is because they saw some extra events that are compatible with signal there. And it's the same story in CMS. Okay, and so the fuss mostly comes from this channel. In fact, there are 2 or 3 channels that really point towards, 2 or 3 sigma of signal. And here you see the Higgs to gamma-gamma energy spectrum, or really the invariant mass spectrum. So you've got number of events versus the invariant mass. And what they've done here is you fit a sort of function through this background. And of course, the Higgs all predicts gamma-gamma spectrum events at 1 invariant mass, so you get this bump at the Higgs mass itself. And so what they've done here is it superimposed 130 GeV Higgs bump on top, and it would give you this sort of red thing here. And of course, the data points are these black ellipses. So there's no evidence you can see, particularly for 130 GeV Higgs, but you can see a little bump here, and that's what the fuss is mostly about. It's around 125, 126 GeV. So now if we look at the p-values, this is the probability, assuming the some model, that the data would have fluctuated to disagree with the no Higgs observation, the no Higgs hypothesis. And so what you see here, so for example, the Higgs to gamma-gamma observed p-value is this red signal. So you can see there's no particular evidence. The probability isn't particularly low until you get to around 125 GeV, and here the p-value is like getting down towards the 3 sigma level at 10 to the minus 3. If you combine all of the experiments, the local p-value gets down towards 4 sigma. But the thing is, there's lots of bins, and this could have occurred anywhere in the plot just through random fluctuations. And when you combine all these things and take them into account, you end up in Atlas with about 2.2 sigma. That's taking into account this look elsewhere effect. So that's not that strong. If you do the same thing in CMS, you get only 1.5 sigma. But of course, no one yet has actually no one's officially combined these two plots and these two significances, but the significances will go up quite a lot because the two pictures are in the same place and pretty much compatible on either side. So this looks very exciting, and we look forward to later on this year. There's going to be an announcement at 9 o'clock in the morning, Geneva time, I guess, so 8 o'clock here, on the 4th of July at CERN, about the Higgs. We don't know what it's going to say. There are various rumours, and I can't speak to their veracity, to their whether they're true or not. But Fernando is going to be there, so he can tell us. He's going to jet over. Okay, so the big channels are Higgs to gamma gamma, as I've already said. Both experiments see this significantly. Then Higgs to ZZ, where one of the Z's is off shell. They both decay into leptons, so you get this 4 lepton signal. There's a couple of sigma in each experiment. And Atlas additionally maybe got a bit lucky and got 2 W's where one of the W's is off shell and decays leptonically, the other one hadronically. That's at 1.4 sigma. Okay, so the question is, does this agree with the standard model roughly in terms of the branching ratios and stuff, and actually the overall cross-section? So this is a plot from CMS, and basically, so the best fit cross-section, of course, if it's the standard model, it should be compatible with 1, and from the experimental results, you get this green band. So you see to within 1 sigma, yeah, the number of Higgs events coming out are about what you expect. Then, if you look in each individual channel, of course, the errors are larger before you combine them, but then you can ask if it's compatible with the standard model. And what you see is that broadly, yes. If anything, the Higgs to gamma gamma is slightly large. It's just, it's 1.3 sigma or something above the standard model expectation. But that could easily be a statistical fluctuation. But that hasn't stopped many people speculating on the theoretical reasons for why that's the case. Okay, so what happens this year? Because of course last year we were at 7 TeV, this year we're at 8 TeV, and if you look at the latest predictions for the Higgs production cross-section in the standard model at 125 GeV, it was about 15 picobarns. This year it's at 20 picobarns because the energy's gone up. But not only does the signal cross-section go up, the background cross-sections go up as well. But your sensitivity is roughly signal over square root of background. So overall, your sensitivity does go up to the tune of about 10 or 20%. So for the same data this year, which actually they have more data than last year already, you expect more sensitivity and to be able to get a few more sigma if the signal remains there. If the Higgs signal goes away, then you'll need to build models to explain that. So for example, models where the Higgs decays invisibly into neutralinos or something, or other particles, or models where the cross-section's suppressed. You can do this, for example, if you make the stop quasi-degenerate with the top, and then in the production cross-section with gluons, there's a loop of tops or a loop of stops, and of course they differ by a sign, and so you can start cancelling some of the cross-section. Okay, so what if this Higgs sticks around? What does that mean for SUSY breaking mediation mechanisms? Well, there was this paper by Abe Battaglia et al., and what they did was they just scanned SUSY parameters, assuming some mediation mechanism, and saw what the highest Higgs mass they could get is. And so, for example, you see in minimal anomaly-mediated SUSY breaking, they could get 1 to 1. So, of course, this depends logarithmically on the ranges of parameters that they've scanned over. the domain of the parameters, but they scan up to several TeV beyond where you would expect the model to be natural in some sense. So if the Higgs signal remains at 125 plus or minus 1 GeV, they say minimal anomaly mediation is ruled out. Also, minimal gauge mediation is out. The CMSSM, or the M-Sugra model, can be accommodated, but this doesn't take into account all of the other constraints that are on the model, so you have to check that indeed you can get dark matter and all the other things to work out as well. So that's an interesting point. Yeah.
What was the range of the parameters they were using?
Well, I can't remember in detail in each one, but I mean, quite a large range. It wasn't. You didn't look at it and go, "Oh, that's restricted." It was up to several TeV in the parameters.
So the question is, how confident should I be with these numbers? I mean, is this a no-go theorem or?
Well, nothing's a theorem here, but so I mean, of course, if you allow to scan up to the input parameters, soft terms of order 10 TeV, then that's not going to hold, right? You can squeeze it up another couple of GeV. But so they went up to like 4 TeV or something. Okay. So some sort of reasonable number. Okay, so let's go on now to supersymmetry. And of course, I've specially coloured this slide so you can't read it at all. So what you have here actually is an event that happened on the 22nd of October last year, which gives you your classic, it fits with classic supersymmetry type searches. It has a missing transverse energy of 984 GeV, which, as you all know, is the smoking gun for usual vanilla supersymmetric events. It has 4 hard jets. One of them's very hard, 974 GeV. And okay, I mean, you can't see very well on here, but there's 4 jets coming out, and the missing ET is going in this direction. The point here is that what you need to ask is all this missing ET coming from mismeasurement of one of these jets? So if the missing energy points along the jet, then it's because a lot of the jet's gone down the crack or something, and or if the missing ET is opposite to the jet, I should say. So the experiments include cuts to do that. But anyway, this is an event where that's not the case, and this looks like a candidate for producing strongly interacting SUSY particles, which then decay into jets and neutralinos. Okay, so one thing that happened last year from Sundram and many others is this so-called natural supersymmetry. So this is this is really bottom-up approach. Okay, so you guys should be aiming for this to sort of batter it. That's the message here. So if you look at the MSSM Higgs potential and you minimize the Higgs potential, very roughly speaking, taking into account the fact tan beta has to be reasonably large, you get this well-known relation between MZ, the mu parameter from the superpotential, and the soft breaking mass MH2, and then MH2 squared gets radiative corrections from the stop. It gets radiative corrections from many MSSM particles, but the largest ones are the ones from the stop, which have the top Yukawa coupling in them as well. And the form of the radiative corrections look like this. So there's some logarithm of a UV scale over m stop. They say, well, suppose that's order 1, and suppose so the question is, if we have some stop mass, there are lower bounds on this now, which are making this thing rather large, and so, but it's got a minus sign, so you can cancel it against a rather large mu term, but there's no a priori connection, they say, between, or at least from the bottom-up perspective, between these two terms, and so that looks rather unnatural. You're organising a sort of unnatural cancellation. So they say, let's take this thing to the extreme and say, where would we expect SUSY to be, and demand no larger than order 1 cancellations. And if you do that, you're going to get a bound. You know what HT is. You're saying this is of order 1, so you're going to get a bound on the stop mass. And not only that, actually, there are large loop corrections to the stop mass from the gluino. You can see this as 2 loop correction to the Higgs mass involving stops and gluinos. And by using the same logic, you can place an upper bound on the gluino mass. So this is extreme naturalness. It's not even order 1 or larger than order 1 cancellations are allowed. So if you do that, what you find is that the stop mass should be less than about 700 GeV, the gluino mass should be less than about a TeV. That's the most natural, from bottom-up perspective, most natural place they can be. Experimental missing ET searches, whenever they apply, tell you that the stop mass is bigger than 500 GeV and the gluino mass is bigger than 900 GeV. And so, this window, this very natural window, is being closed. Okay, so those searches come from those limits come from these searches. Here's where you have protons going into gluinos. The gluinos decay into a T bar and a neutralino, and then the tops go on to decay and stuff. And you just look for these 4 top final state. The intermediate stops may be on shell or off shell. It actually doesn't matter much. Here's the bound that you get. So this is about 800 or 900 on the gluino mass, and about 500 on the stop mass if it's on shell. Okay. So what about the Higgs? That's the other question in the MSSM. Well, we know actually from work. Actually, I didn't reference this. This is Barbieri et al. Back in post-LEP days, so 10 years ago. He plotted the MSSM fine-tuning parameter. This is the sensitivity parameter, d log mz squared by d log parameter, which tells you how much of this cancellation you have to do. And so the red points are what you want to be looking at. And what we see is that when the Higgs mass already gets above the LEP bound, you're going to fine-tunings in the MSSM of 25 or above. So this wasn't taken into account in the previous plot, and if we go up to 125, we can see fine-tunings of 40 or 50. So if you really, you may not worry about that. Maybe fine-tunings of 1 in 100 is fine, or even 1 in a few hundred. At some stage, you begin to get uncomfortable. But one way you can get beyond this is to build your string model to reduce the fine-tuning. This is like from a weak scale bottom-up perspective, as was the previous slide, but of course you can organize cancellations in fine-tuning or special circumstances from your string model which give you specific patterns of SUSY breaking terms. So that's one thing you could be aiming for. The other thing you can do is build in a singlet, and this is becoming very popular with the phenomenologists now. So the next to minimal supersymmetric standard model makes it very easy to get quite a few extra GeV for your Higgs mass and keep the fine-tuning down. So that's one good thing you could do. All right. So let's now look at the supersymmetry searches. Jets plus missing ET search. Well, what that tells you is what you plot on the squark mass and gluino mass plane. You set everything else heavy apart from the neutralino, which is approximately massless, or 100 or 200 GeV, but not too heavy. And what you find is that masses under 900 GeV for the gluino and under 1200 or 1300 GeV for the squarks are ruled out. But you should bear in mind that because you're colliding protons, these are really not bounds on the stop or the bottom, they're bounds on the first 2 generations of squark mass. So, this is telling you that naturalness is under pressure. We expect light gluinos and light stops. But we notice that this is really a bound on the first 2 generations of squarks. So you could get away, there's still a window left where you have the gluino in this mass range, which is like a very natural spectrum, the stop mass in this range, 0.5 to 0.7 TeV, and the neutralino mass lighter than the stop, basically. That's a very natural region. That could well be ruled out very soon, for example, this year. So let's be pessimistic and say it is ruled out rather than discovered. How can you get around it and still keep extreme naturalness or very natural spectra? Well, you can compress the spectra. So this is another thing you can organize in your models. You can try and get quasi-degenerate spectra out, which are not hierarchical, but where the squarks and the gluinos and in particular the neutralino are not too split by mass. Because in that case, when a gluino decays into squark and chucks out a jet, the jet doesn't get much energy. And there's always minimum energy cuts on the jets. And so if it doesn't get much energy, it will fall under the jet cut, and the searches that were applied won't apply to your model. So that's one way to get around it. One way that we've been looking at is that you can build in R parity violation, which means that you have to find dark matter from somewhere else than the neutralino. But if you build in R parity violation, basically the searches don't apply because you remove the missing energy from your predicted events. So it would explain why natural SUSY hasn't been found yet, and well, we showed that actually like-signed dileptons is a generic signature no matter what coupling you choose. Okay, so here's an example. So you produce gluinos, they decay via stops, which of course are light, and then you have this R parity violating interaction which gives you jets, and there's no like stable neutralino-like object. So this is just an object with 6 jets. That's not easy to discriminate from standard model backgrounds, and you have to do something special to look for it. Okay, so now let me go on to an anomaly at the tevatron. This has been around for quite a few years now. I'm sure you've heard about it. It's a forward-backward asymmetry in anti-top production. If you look, C is cos theta, where theta is the angle between the top and the proton. And you look to see how many tops go in the proton direction. Tevatron's colliding proton, antiproton. How many tops go in the proton direction when they come out compared to how many go in the antiproton direction. So the standard model prediction comes from an interference between this tree level and one loop QCD diagram, and it's about 6.6%. And what both experiments are measuring now is something like 15, 16, 17%. Thank you. In fact, so that's like a 3 sigma discrepancy in each experiment. And the effect seems to increase with invariant mass of the TT bar pair, and it's currently not understood where this comes from. So this is an interesting thing to keep an eye on and may require some model building. And it's more weird than that, because if you've got basically the angular distributions of tops coming out don't seem to agree with the standard model expectation. So maybe it's new physics, but then new physics, your naive expectation would be that there's some extra interactions which increase the amount of TT bars coming out, and that's not the case. The cross sections both at the LHC for TT bar production and at the tevatron more or less agree with the standard model predictions to within a sigma or 2. Not only that, the shape with the invariant mass of the TT bar also agrees. So there's quite a lot of experimental constraints if you want to build a new physics model to explain these angular distributions. So then the question is, of course, tevatron's shut down. So what about at the LHC? Can you test this experimental effect? Well, it's very difficult because, of course, now you're colliding proton-proton, so you've got no kind of anti-proton direction to discriminate between the two. But what you can do is devise a charge asymmetry which is similar. You can say, how often do the tops come out closer to the beam compared to closer than the antitops? And build an asymmetry on that, and you get some prediction which is consistent more or less with the standard model prediction. Sorry, this is the measurement and that's the prediction. And so this is another constraint that you have to fulfill. Anyway, Schroeder and I have been working on this recently, and we think with R parity violation, with the same kind of couplings we were looking at before, you can satisfy all these constraints and get the forward-backward asymmetry to come out. So that's kind of an interesting point. Okay, in B physics, switching to B physics now, one thing that's going to impact you is this branching ratio, rare branching ratio, B sub S into mu plus mu minus. This one is very small in the standard model prediction. There's a penguin diagram, there's Z top and Z mass suppression, and the prediction is like 10 to the minus 5, 3 10 to the minus 9. And now finally, after only putting upper bounds, they've got a tentative signal which is a bit lower than the standard model prediction to the tune of a sigma or 2. And it looks like more like 1 10 to the minus 9. So the point here is that in the MSSM, especially at large tan beta, the diagram with the pseudoscalar Higgs here and a chargino and a stop in the loop contribute. And so you get bounds on the parameters that are involved here by this experimental bound. So the branching ratio is less than this number, thank you. And so you better not have too large tan beta or too small MA at the same time if the stop is reasonably light, as you expect from a natural spectrum. Otherwise you'd be ruled out. Sorry?
Where's this signal coming from?
So this is LHCb. This is 1 inverse femtobarn of 7 TeV LHCb data.
So it's more recent than the 4.5 times 10 to the minus.
No, so that's the same. So this is, if you work out what the upper bound is from this measurement, then you get this number.
Oh.
So it's like if you add like 2 sigma onto this, roughly, you'll get more or less. Okay, so now I've just got a few minutes to talk about this gamma ray line. So this is the Fermi-LAT satellite, which measures galactic gamma rays. And basically, they haven't found any particular signal. Dark matter annihilation, for example, this one would give you a monochromatic gamma ray line. So you might have some continuous background, but with a bump on it corresponding to annihilation of dark matter particles. But Veniger reanalyzed the data and optimized the regions of the sky that he looked at, setting down some model of how the dark matter density varies in the galaxy. And then, so he was trying to maximize the significance of a gamma ray line. And he found, with 3.3 sigma evidence, a gamma ray line at 130 GeV. The rates predicted by some diagram like this are too low. The branching ratio, or sort of, needs to be sort of 5 to 8%. And the problem, that's the branching ratio of this final decay. And the problem is, because these initial dark matter's chargeless, usually, unless you do something special, this has to be a loop suppressed diagram. And so you'd expect kind of per mil or lower branching ratios here. So this could be something strange, or actually plenty of models have been built. You can get around this easily, which give you approximately monoenergetic photons. So this first paper told you actually that it depends, the way he did it depended on the dark matter density that you assume in the galaxy. But then Finkbeiner and Su came out and just used the data itself to extract this gamma ray line. So the gamma ray line is supposed to be in this, it's 130 GeV, right? So it's supposed to be in this energy window. So all they do is they average the other ones, the other maps. This is the power spectrum of the radiation, and they subtract the average of these from the this energy bin, and you end up with this map. And so what you see is that this 130 GeV line is dominantly coming from near the center of the galaxy. Now that radius is about 4 degrees or so, and so that's significantly away from the center of the galaxy as well. So this is quite interesting. And then they refit the data, allowing a sort of cusp with large dark matter annihilations in the center of galaxy, fit all the different other features that you know. And for the other features, you just see a flat photon spectrum. But for this cusp, you do see about 130 GeV, some excess. So all of these arrows are just saying upper bounds. So there's no evidence in the cusp for high energy gammas, but only gammas here, possibly a second line here. So this is the evidence here is at the 3.7 sigma level once you take into account the look elsewhere effect. So this is something interesting to take account of. And so now, just my final topic is just to round up neutrino oscillations. We already know quite a lot about the neutrino mass parameters. There's a small mass splitting associated with solar oscillations, a large one associated with atmospheric, a large mixing angle for the solar here. And once you know these three parameters, actually you can measure the last mixing angle in the neutrino mixing matrix, which is this top right-hand one. It's the mixing, it's the W coupling to an electron and the third heaviest neutrino that you're interested in. It was a strict tri-bimaximal model which predicted a zero there. And all you have to do, once you know these parameters, is produce electron neutrinos in a reactor. You let them travel and find out how probable they are to survive. So you have near and far detectors, and that's what Deobay did. And the only thing you don't know in this expression is theta 1,3. So you can end up finding out this probability and then fitting theta 1,3. And what you find is that it's over 5 sigma away from 0. All of the previous experiments were kind of pointing in the same direction, apart from maybe Show, but they weren't very accurate at all. They're only kind of 1-2 sigma level measurements. Okay, so to wrap up, all eyes on the Higgs boson, 4th of July, a week on Wednesday at 9 a.m. Geneva time. The minimal SUSY standard model is under naturalness pressure from Higgs and other results. This is an opportunity, I think, for string model builders. SUSY is only natural if you only in the MSSM if you have either compressed spectra or R parity violation, or there's still this window with certain particles light and other ones heavy. Gluino, stop, neutralino, chargino, first two generations of leptons, you might put light. So the Tevatron TT bar forward backward asymmetry stands out. Of course, we'll have no more data on this from the Tevatron, but it's worth keeping an eye on the LHC charge asymmetry to see if something transpires there. And there's this potential 130 GeV gamma ray line in Fermi-LAC data, so keep an eye on this, for developments on this. We could have more data within the coming years. Thank you.
Hi. So, can you go back to the R parity, the TT bar asymmetry slide with the R parity?
Yeah, TT bar asymmetry, yeah. What,
so
this
yeah,
one?
that one. Yeah. So, what masses do you need?
Yeah, so the spotum comes out, actually I've got a plot, I think I put it in the auxiliary information. The spotum comes out between 300 GeV and say 1.3 GeV. This coupling has to be rather large. The R parity violating coupling is larger than 2 for this to work.
But this would be ruled out by other indirect bounds, no?
No. Well, it depends. If you have all of the other SUSY particles light, then it would be. But this is, we've said, look, let's do bottom up. So we'll only have, say, the spotum and the stop light, and then it's fine. So if the other ones
large
are
coupling is fine.
Yeah, with that large coupling, of course we check that. Yeah.
This one's consistent with the CT bar charge asymmetry measurements?
Yes, yes. What you can see is this is the beyond the standard model contribution, this colour, and in this orange region here, it's consistent. And we've applied all the other constraints, and you get this sliver here, which is consistent with everything.
You haven't mentioned anything about extra dimensions. I think experimentalists are also interested in finding Kaluza-Klein particles.
Absolutely. So there are many experimental searches looking for those. No signals yet. But they look for discrete, kind of Randall-Sundrum type gravitons, for instance, and also, infinite tower or semi-infinite towers of Kaluza-Klein gravitons from large extra dimensions, all that, and monojet signatures. There's a whole slew of signatures that they're looking for, but they haven't found anything yet.
Oh, all questions seem to be answered. Thank you very much.